Hi everyone, Mr. Bowman here. We are going to continue our exploration of right triangle trig with more applications. So we're going to start section 6.1 here, and section 6.1 is about vectors. And for those of you who have taken or are currently taking a physics class, you probably already have had some exposure to vectors. For those of you who haven't, just pay close attention. So what is a vector? A vector is a quantity that has a magnitude and a direction. And like almost everything that we do in math, we can represent it with a visual, and the visual looks something like this. We can draw vectors wherever we want, and when we draw vectors, we draw them as a ray. We put a letter above them, which is going to either be boldface, which I can't do very well on OneNote, or it's going to have a line segment above it, or a line segment with an arrow above it. So vector v, for example, shown there. If we put the vector originating at the origin, it's called standard position. So I'm just going to move vector v down here. And as long as it has the same direction and length, then it is equivalent. So when we draw vectors, the magnitude is represented by the length and the direction by the angle. And to be clear, we typically measure the angle the same way we measure angles using trig, with the initial side of the angle being the positive x-axis and the terminal side being formed by the vector itself. Obviously, when we draw a vector like this, we can break it down into a right triangle and find its horizontal or x component and its vertical, its y component. To indicate that it's a vector, we use this notation instead of parentheses. We have that left arrow or less than sign sort of thing, the x component, the y component, and the right arrow. And the magnitude or the length of the vector is represented as such. So there's vector v, and we put these what look like absolute value signs around it, and it's the hypotenuse of the right triangle. So obviously it's the positive square root of x squared plus y squared. So vectors can be specified in various ways, and one of the ways that they can be specified is like this example here, where the starting point coordinates are given and the ending point coordinates are given, and the starting point is called the tail and the ending point is called the head of the vector. And what we'd like to do is we would like to figure out how long is its horizontal component and what direction is that, how long is its vertical component and what direction is that. So you can take the vector as it's shown here and you can break it down into its vertical component, which is downward because we would move from tail to head, and its horizontal component, which is to the right, which makes that positive like that. Or you could take that vector and you could move it into standard position and translate that information, and you could see that its horizontal component is positive and its vertical component is negative. But there's a quick way to find the magnitude and direction of the horizontal and vertical components. It's basically take the x-coordinate of the head and subtract the x-coordinate of the tail, and that will give you not only the length of the x component but the direction, so that is 5. And do the same thing for y. The y coordinate of the head, 1 in this case, minus 8, the y coordinate of the tail, and that obviously is negative 7. So that gives you the vertical magnitude and direction, and then we simplify that to 5, -7. And obviously those two components are always going to form a right angle, so we can use those to find the length of the vector, or the magnitude, or the hypotenuse of the triangle that we form. And we are going to call this vector v, so I'll put a v over there with a line above it, and its magnitude is given by the square root of 5 squared plus -7 squared, the positive square root of that, which is the square root of 74. The direction angle is going to tell us the direction part of the vector. And the easiest way to visualize this is to take the vector and move it into standard position, which means that the tail is at the origin. So if you do that, if you put the tail at the origin, I'm going to switch colors here. If you put the tail at the origin and you still have the same horizontal and vertical components, you can find the direction angle, which I'm going to call theta. So our horizontal component is still 5, our vertical component is -7, and we know by looking at the diagram the tangent of angle theta is equal to, by definition, y -7 over x 5. And we typically give these angles in degrees, so using the inverse tangent function, we get the following. Tangent inverse of -7/5 is going to give us an angle of -54.46 degrees. You can measure it that way, or if you prefer, you can go the other direction around counterclockwise, and obviously to get that answer you would just add 360 degrees to that negative number, so that would give us 305.54 degrees. Either one is acceptable. Sometimes instead of using a single letter for a vector, we use the letters that represent the tail and the head. The way that it's written, the tail would be first, the head would be underneath the arrow of the ray. So what this tells me is that R is the tail and S is the head of the vector, and the head is at the arrow end. So our vector is going to point in this direction, and we want to now find the component form of that. So obviously we're looking for the magnitude of the horizontal component and its direction. Same thing for y, the magnitude and its direction. We can see that the x component has a negative direction, the y component has a positive direction. So how do we find component form? Like we did a minute ago, and we're going to take the x coordinate of the head, -1, minus the x coordinate of the tail, 4. Do the same thing for y, 6 minus 3. Simplify that, -5, +3, and check to make sure that that makes sense. Your x component is in a negative direction, so -5. Your y component is in a positive direction, +4. And then to find the magnitude of this vector rs, we are going to use the Pythagorean theorem. So -5 squared plus 3 squared. Take the square root of that, and we have the square root of 34. The direction angle we can find the same way we did with the previous problem. Basically, what we're thinking here is, what if this r were at the origin? What direction would this vector be pointing? So to make that easier to imagine, I'm going to move this vector rs over here, and point R is now at the origin and S over there, and we can see that the direction angle is going to be somewhere between 90 and 180 degrees. Well, just like we would with right triangle trig, we would find our reference angle, so we'll call our reference angle theta, and we have a horizontal component of -5, a vertical component of +4, and we are going to write the tangent of theta is equal to y over x, and use the inverse tangent function in degree mode, and we get theta is equal to inverse tangent of 4 over -5, and that gives us an angle of -30.96 degrees. Now, if you are thinking that you did something wrong, you didn't. Okay? What you have to know is that the inverse tangent will always give you an answer between -90 and +90. So what it just gave you is this angle over here of -30.96 degrees, and that's why you have to have a good picture of this. So the angle that we really want, we will call that angle phi from the positive x-axis counterclockwise around to vector rs. Angle phi is going to be -30.96 degrees plus 180 degrees, which is going to give us 149.04 degrees. Or if you prefer, you could specify it as the negative version of that, but I think being consistent is easier, starting at the positive x-axis and going counterclockwise. If you do that consistently, you're less likely to make mistakes. So what are equivalent vectors? Equivalent vectors are vectors that have the same magnitude, length, and the same direction. And one of the ways that you could verify that two vectors have the same magnitude and the same direction is to take one of the vectors, let's say we call this vector A, and slide it without changing its length or direction and move it over on top of vector B and see if they lie directly on top of one another with the same direction, not in opposite directions. Well, that's impossible to do in this situation, so another way to do that is to compare their component forms. So vector A would be given by, remember, we're going to take head, h minus tail, and vector A would be given by 1 minus -2, or 1 plus 2, and 2 minus 6. So when we simplify that, we have 3 -4. And think about that. Does that make sense? Is the horizontal component in the positive x direction? Yes. Is the y component in the negative direction? Yes. So that seems reasonable. And then we can do the same thing for vector B. Remember, head minus tail. And so we're going to take 3 minus 0 and compare, and -4 minus 0. Simplify that, 3, -4, and compare those. And you see they have the same horizontal and vertical components, which means that they're equivalent. And you could verify that if you moved vector A so that its tail was at the origin, it would lie directly on top of vector B, which means they would have exactly the same length and exactly the same direction. So the next thing we want to do is talk about adding and subtracting vectors or multiples of vectors. So vectors can represent things like forces, and because you can have more than one force acting on an object, we want to be able to figure out the effect of all the forces. So what we do is we add vectors, and it's a little hard to tell here, but U and V are bold, but I'm going to put arrows above them to represent the fact that they are vectors, or segments above them to represent the fact that they are vectors. And what we're going to do is we're going to start out by drawing vector U and vector V in standard position. And then we're going to say, well, what would happen if we added those two vectors? So over here to the left, I'm going to draw a vector u, which has horizontal component 2, vertical component -4. So vector u looks about like that. And vector v, I'm going to do that in blue in standard position as well. It has horizontal component 3, vertical component -5. So it's going to be more like that. So about like that, vector v. And the question is, what would happen if we added those two? Well, if you imagine those as forces, they're kind of pushing in the same direction. So the overall effect is going to be a bigger force in the same direction. And as far as adding them is concerned, basically what we do is we add them head to tail, so to speak. So since we can move a vector wherever we want and it's still equivalent as long as we don't change its magnitude and direction, what we're going to do is we're going to erase vector v here and we're going to draw it over here added to vector u. So here's vector v, and the resulting vector drawn in standard position will be the big green vector. So it forms a triangle. And you could tell that the green vector has a positive x component, which consists of both of the x components of u and v, and a negative y component, which consists of both of the y components of u and v. So what it comes down to is quite simply that when you are adding vectors, you add the horizontal components, you add the vertical components. So vector u plus v would be 2 plus 3 for x, and -4 plus -5, or -4 minus 5 for y, which is going to give us 5, -9, which you can tell by looking at that green vector there that that seems pretty reasonable. In a similar way, subtracting vectors, so we take one vector minus another vector. Well, a way that you can think about that is taking vector v and adding the opposite of vector u. And the opposite of vector u means that it actually points in the opposite direction. So if you thought about that for a second, what would cause vector u to point in the opposite direction? Well, change the sign on its horizontal and its vertical components. So vector v minus vector u can be thought of as taking vector v and adding the opposite of vector u, which is simply just taking the horizontal component of vector v and subtracting the horizontal component of vector u. So we would have 3 minus 2 for the horizontal component, and -5 plus 4, which would give us a result of 1, -1. If you would like a visual of that, it would look something like this. We're going to draw vector v in standard position, so over 3 to the right, down 5, here's vector v, and then we're going to add the opposite of vector u. So vector u is going to go back the other way, 2 units to the left and 4 units up. So it's going to put us over here. It's a little hard to draw there. And that is going to result in this new green vector, which is going to have horizontal component +1 and vertical component -1. And then the last thing that we want to do is talk about, well, what if you were to multiply a vector by a number? What effect would that have? Well, multiplying a vector by a number stretches it and does not change its direction unless it's negative. It does not change its direction any other way. So if, for example, in number 3, we are going to take 2 times vector u. Well, what does that do? It keeps the same direction as vector u, but it doubles its magnitude or its length. 4 times vector v keeps the same direction as vector v, but it makes its magnitude 4 times greater. However, we have a negative in front of that, so the negative is going to change the direction overall. So how do we deal with that in component form? we simply do the following. We say 2 times 2 negative 4 minus 4 times 3 negative 5, and we distribute first because multiplication comes before addition and subtraction. So we have 4 negative 8. That would be a vector, same direction as vector u, except twice the magnitude. We're going to leave the negative here. 4 times 3 is 12. 4 times negative 5, negative 20. That would be a vector in the same direction as vector v, but 4 times the magnitude. And now we're just going to do the subtraction. So we have 4 minus 12 for the horizontal, and negative 8 minus negative 20, or plus 20 for the vertical, for an overall vector of negative 8 in the x direction and positive 12 in the y direction. And if you wanted to, you could draw a vector twice the length of vector u and add to it a vector 4 times the length of vector v, but change the direction to the opposite for vector v, and you would see you would end up with a vector of negative 8, positive 12, which would put us with the head of the vector in the third quadrant. And we are going to finish up with the following. If you're given the magnitude and the direction of a vector, you can find its component forms. So what we do is we draw the vector in standard position. Tail is at the origin, with the angle or direction being measured from the positive x-axis in a counterclockwise direction. So vector v has a magnitude of 12, so we're going to make this 12 units long. Magnitude of v is equal to 12, and its direction angle 40 degrees, and we want to break it down into its horizontal and vertical components. So we are finding the horizontal component, the x, and the vertical component, the y, and we have some simple right triangle trig here. So x, y is equal to the magnitude of v times the cosine of theta, and y is the magnitude of v times the sine of theta. Now, I want to show you where that comes from. If we were to find the cosine of theta in this situation, we would have x over the magnitude of v, because the magnitude of v is the hypotenuse. So if we were to multiply both sides by the magnitude of v, they cancel out on the right-hand side, and we have our horizontal component. Similarly, the sine of theta is equal to y over the magnitude of v, and if you were to multiply both sides of that equation by the magnitude of v, they would cancel out on the right-hand side, and you'd have your answer. So for us, our component form is going to be 12 cosine 40 degrees and 12 sine 40 degrees. Make sure you're in degree mode, and if you check that out, you get approximately 9.19 for the horizontal component and 7.17 for the vertical component. And if you wanted to check that, you could say, well, let me double check that. I should get, for a tangent of 40 degrees, y over x. Also, you could square both of those, add them, take the square root. You should get an answer very, very close to 12. And for the last one, we have a magnitude of 6 and a direction angle of 115 degrees. So from the positive x-axis, counterclockwise, we have the following. Vector v has a magnitude of 6, and this is 115 degrees, and this is why you want to be comfortable with reference angles. If the angle shown is 115 degrees, then the reference angle is 65 degrees, and our vertical components and our horizontal components are as such. And so x and y, again, xy is going to be equal to the magnitude of vector v times the cosine of the direction angle, and the magnitude of vector v times the sine of the direction angle. Now, interestingly here, you can use 115 degrees and it will give you the correct sign. In other words, x is going to be negative and y is going to be positive. Or you can use 65 degrees, but if you use 65 degrees, you're going to get a positive number for x and a positive number for y. So then you have to make sure that you adjust because x is definitely negative. In either case, you will get the following result: negative 2.54 for x and 5.44 for y. Check it both ways and make sure that you understand what I was saying there, and this is the importance of drawing a picture. So we are going to talk more about vectors and applications of them later on, but before we do, we have to make sure that you understand this. Have a good day, everybody.